push that I need to have pushed. And it looks like you guys have the document camera on there. All right, so what we've been talking about is rotational motion. Now remember that rotational motion, ooh, that's a bad sign. Everybody knows that the more perfect circle you are, the more disturbed you are, right? It's Friday, my circles are really nice today. So that's one of the things we got to worry about. That we call this direction positive, and we've done that. We've had the change in angle with respect to the change in time is going to be our angular velocity, and our change in our angular velocity with respect to time is our angular acceleration. We can have the same kinematics equations that we've had before, but we're dealing with them in an angular sense. Those are our kinematics equations, and we can have those aspects. And we talked about that we're in radians, so we go from 0 to pi to 2 pi. And we got to make sure our calculators are in the right units when we do this. So we got to make sure of that. And we started talking about the fact that we have something that we're going to call a right-hand rule, because that is a vector quantity. Okay? That is it's a vector quantity, and we've got the right-hand rule, and like all vectors, vectors have magnitude and direction, and so we end up dealing with where our vector quantity is going. So the right-hand rule is going to go like this. If my motion is in the circle in the positive direction, I'm going to put my fingers along the side of the motion, and I'm using my right hand, because right hand is, our hands are chiral, and don't fall into the trap, because on a test you will fall into this trap. If you are right-handed, you'll be doing this, and you'll be doing the right-hand rule with your left hand. That is a trap, because that's going to give you the wrong direction. Your correct direction is going to be based off your right hand, and if my fingers curve, the angular velocity is going to be coming out of the paper. If I happen to be going clockwise, my angular velocity is going to be going into the paper. And what we're going to see on Wednesday is that becomes very important when we deal with torque. Okay, when we deal with torque, because torque is also a vector quantity, and remember that work, we did force dot distance, and remember that became our force dot cosine of the angle, right? Remember that? And this was a scalar quantity. This is force acting through a distance. Okay? This is through a distance. It's a scalar quantity. We lose the direction. Even though this is in Newton meters, we defined that as a joule, and this was related to energy. Torque is going to look a lot like that, except torque is a vector quantity, and my vector quantity, we do what is known as a cross product or a vector product. So this could be called a scalar product, this can be called a vector product. And this is force acting at a distance. This is force through a distance, this is force at a distance. And even though, if we say the maximum torque, okay, the maximum torque is going to be RF, and even though we write it FR, the order of the function is very important because of the right-hand rule. right? The order of our function is extremely important for the vector quantity because of the right-hand rule. And that's why if I have a screw, so I'm going to try and draw a screw here so that we know what we're dealing with. If I have a screw and I am using my screwdriver, if I turn my screwdriver this way, it goes in, or if I do that this way, it's going to come out of the hole. If I go clockwise, it's going to go into the hole. Righty-tighty, lefty-loosey. And it's because the same reason that I'm going to get and if I draw my little circle here, if this is rotating this way, my angular velocity is coming up. If I'm rotating it this way, my angular velocity is going down. And so for torque, it becomes very, very important to make sure we've got our right-hand rule correct. And this is also going to give us, when we start doing a few other things, as we get to electricity and magnetism, for those of you who go on to Physics 2, you're going to see that gives us our motion of a charged particle in an electric or a magnetic field. Because we're actually going to see motion moving down the field. So we end up with that right-hand rule. So that kind of sets us up for the next chapter, but we want to make sure that we've got what our direction of our angular motion is. So we're going to go back and we're going to look at Newton's law of gravitation just a little bit, because this gives us back to our centripetal acceleration. Remember, we said my total acceleration was going to be equal to my centripetal acceleration plus my tangential acceleration. I'm going to get a total acceleration as I'm going around the circle at my centripetal acceleration. And we saw before that if I'm going around a curve, I'm going to get my acceleration towards the center of the curve to be my centripetal acceleration. So we can get back and get to those things and look at a variety of different pieces. And my force due to gravity is related to a centripetal, and this is a proportional sign. Okay, this means proportional. Is proportional to my centripetal acceleration. And we've shown this a couple of times, that that's v squared over r for my centripetal acceleration. So we talked about it a while ago. We talked about Kepler's laws, that what Newton was trying to do when he did F is equal to g m1 m2 over r squared, that this related back to observations for the Earth-Moon system that he was trying to explain based off of Kepler's laws. And remember, the Kepler's laws were that things are traveling in an orbit. The sun is located at one focus of the orbit, and the time that it takes me to go from here to here, and the time that it takes me from go to here, if those two times are the same, the areas of these triangles ultimately are the same. We get the area of those triangles being the same. But one of the critical things was, and it kind of helps lead to this right here, that the nominal period squared is proportional to the nominal radius cubed. And that meant we could do that t squared is equal to some constant, big constant k, r cubed. And it turns out that this big constant k becomes 4 pi squared big G m of the sun ultimately equals our k. That's what it turns out to be. But we're going to look at this a little differently and kind of show how this works out. So we're going to go from the Earth-Moon system here. And this is a fun derivation. For those of you that like derivations of things, which was me. I love the proofs in geometry. That was like one of my favorite things in the world. So if I have my centripetal force associated with the Earth-Moon system, this was going to be the mass of the moon times my centripetal acceleration. And we know that centripetal acceleration is v squared over r. Okay? Let's see if I can do this without messing up too much. And now we know from Kepler's law that t squared is equal to is proportional to our radius cubed, and our period is proportional to the square root of r cubed. Now my acceleration is going to be the centripetal acceleration squared plus the tangential acceleration squared. My tangential acceleration, which we've seen is alpha r, where that's my angular acceleration. We know that alpha is my change in my angular velocity. Right? So I can rewrite my angular velocity as alpha t. This is a change in angle with respect to time. This equals 2 pi over the period. Okay? That equals 2 pi over the period. Well, if I look at this a little differently, I know my period is proportional to the square root of r cubed. So that's going to be something that I'm going to come back in here. So I'm going to come back to this. So my centripetal acceleration is v squared over r. But we know v squared is this right here. So this becomes r omega squared. But we just showed that omega is this 2 pi over there. So this becomes r 2 pi over the period squared. So now that becomes r 4 pi squared divided by the period squared. But we can do that as r 4 pi squared r cubed. That cancels, and I get 4 pi squared r squared. We're off by a constant, of course. But I can look at it from that perspective. So now, if I go back and I do A is equal to the square root of my centripetal acceleration, okay? This is 4 pi squared r squared. And I have my tangential acceleration. So we're going to come back here. My tangential acceleration was alpha r. And if I look at my alpha r, okay, my alpha r, remember alpha is going to equal my change in omega with respect to time, and that's times r. My time is my period, and my omega is 2 pi over the period. I have 1 over the period, and I have r. So now I get 2 pi t squared r. But my t squared is an r cubed, right? So I get 2 pi r squared for my tangential acceleration. So now I get alpha, or my A is I forgot to square that. I forgot to square that. So it becomes 4 pi squared r squared plus 2 pi r squared squared. So I'm going to end up with 1 over r squared, because if I get an r squared plus an r squared, I can factor that out. The square root of 16 pi to the 4th plus 4 pi squared. But that, again, we're off by a constant, so I can make that just a constant, and I get c over r squared. So now I can go F of our centripetal acceleration is the mass of the moon, c over r squared. And that constant that Newton actually shows is that that c becomes the gravitational constant mass of the sun, mass of the moon, over r squared. Hang on, I can't, I tried to push it up and it just didn't want to go up. So we can use our circular motion to really, really help us understand orbits and how orbits come into play. All right, so now we're going to complicate things. Well, let's start with this one. That one's going to be easier. Okay. We have a car traveling around a turn. With a radius of 30 meters and a speed of 5 meters per second. We want to calculate the centripetal acceleration. And then, as the car enters the second turn, has the same radius, the car is going to accelerate. To 7.5 meters per second in 2 seconds. Now we want to calculate the tangential acceleration, the centripetal acceleration, and the new angular velocity. So my first thing is the centripetal acceleration is AC is equal to V squared over R. We go in at 5 meters per second. We have a 30 meter square. We have a 30 meter radius. That becomes 25 meters squared seconds squared divided by 30 meters. Meters cancel. I've got an acceleration. That makes me feel good. And I get 0.83 meters per second squared. My tangential acceleration is going to be my change in velocity with respect to time. So I'm going to go from 7.5 meters per second minus 5 meters per second divided by my change in time, which was 2 seconds. This gives me 2.5 meters per second divided by 2 seconds. That's going to give me 1.25 meters per second squared. I need my new centripetal acceleration. That's 7.5 squared divided by my 30 meters. I love it when my notes have two different problems in there. That's okay. Gives you a chance to catch up writing. That gives me 1.875 meters per second squared. So what we've got is A tangential was equal to 1.25 meters per second squared. A centripetal now is 1.875 meters per second squared. We want our new angular velocity, which is going to be just V over R, which is 7.5 meters per second divided by 30 meters. Gives me 0.25 1 over seconds. And now if I want to do my total acceleration on the vehicle, I'm going to get the square root of 1.25 squared plus 1.875 squared. And I get 2.25 meters per second squared. Oh, which one do I want to do first? Okay, we're going to do this one first. Okay, we're going to have a pendulum here. And I'm going to give myself an angle, and I've drawn this a little bit out. We're going to go off with the velocity in that direction. So I've got, the way the problem says that one end of a cord is fixed. We got it fixed, right? It's attached to the ceiling, attached to my finger, attached to something, is fixed, and we have a 0.35 kilogram object, 350 grams, is attached to the other end, where it swings in a section of a vertical circle of radius 3 meters. Okay, we got radius of 3 meters. When the angle is at 30 degrees, so we're going to give our angle 30 degrees here. The speed is going to be 4.0 meters per second. At the instant that this happens, we want to find the tension of the string. We want to find our radial acceleration, or radial or centripetal acceleration. We want to find our tangential acceleration. We want to find the total acceleration. Okay? And we want to find the angle associated with the total acceleration. So not only do we want to find the magnitude and the angle. So first thing we got to do is we got to look at what's happening to our object here. Okay? So I'm going to have tension in the string. Okay? which is going to give me a force that's radial, because my other force that I have in here is the force due to gravity. So I'm going to have a force tangential, force radial, tension in the string, force due to gravity. So I have to set up a force balance. Okay? My force balance, because this is in motion, is going to equal the forces in the radial direction, mass times my radial acceleration, which is my centripetal acceleration. My sum of the forces in the radial direction is the tension minus, and if I look at this, and this is, remember I've got these angles here, okay? That angle is going to be 30 degrees. So this is going to be mg cosine of my angle minus is equal to mv squared over r. Since I know mass, I know gravity, I know velocity, I know radius, I can solve. So tension is going to be mv squared over r plus mg cosine of the angle. I can plug in my numbers. This gives me 0.35, my 4 meters per second, divided by my 3 meters, plus 0.35, gravity 9.81, cosine of 30 degrees. This gives me 1.87 newtons. This one gives me 2.97 newtons for a total of 48.4 newtons. So we find the tension in the string. Well, A sub r is just v squared over r. So that's going to be 4 squared divided by 3, which gives me 5.33 meters per second squared. And that direction is towards the center of the circle. Okay? That direction is towards the center of the circle. So it's going to be inward. So now if I want to find the acceleration tangential, I've got to do my tangential forces. So force tangential is going to be mg sine of the angle, which is going to equal ma tangential. Excuse me, a tangential is equal to g sine of the angle, which is going to be 9.81 times the sine of 30 degrees, which is going to give me 4.90 meters per second squared. And that direction is in the same direction as my tangential force, so it's going downward. But it's tangent to the circle. My total acceleration is just going to be the square root of 5.33 squared plus 4.90 squared. And if I do that calculation, I get 7.24. And that's meters per second squared. And I'm going to do the same thing that I've done before. I'm going to get that tangent, that arc tangent of my angle, which is going to, my arc tangent of my components, and that's going to be, I'm going to do it this way, tangent minus 1 of my 4.9 divided by my 5.33, and that's going to give me my 42.6 degrees. All right, we're going to do the banked car thing. Because we deal with banked cars all the time. That's why highways are banked, so that we can have these right types of curves. So if I have my car on a, and I'm going to drive it on a little, we're going around the curve, okay? So if I have my motion here, I've got my force due to gravity, and I have my normal force, right? We've got our normal force. And we've shown this before, that whatever angle this is got to be that angle right there. So when I write this out, mass times my acceleration is going to equal my sum of my forces, which is going to be my normal force plus my force due to gravity. But that's the overall equation. I'm not accounting for direction or anything in this one. So let's account for the direction in terms of the normal force. Or we can do this in terms of, we're going to do this in terms of x and y. So we're going to start with y first. So my normal force, because I'm not moving in the y direction at all. Okay? I'm in equilibrium in the y direction. I'm going to get my normal force times the cosine of the angle, because that's going to give me this projection. Right? So this is the normal force cosine of the angle. Minus my force due to gravity has to equal 0. So the normal force that we're going to get is just the mass due to gravity divided by the cosine of the angle. Okay. Now if we do the horizontal components, okay, the horizontal components is going to be and the horizontal components, let's see how I want to draw the picture. It's going to be this way, and this is going to be n sine of my angle. I end up with my centripetal force is going to equal the normal force sine of the angle, which actually equals mg sine of my angle divided by cosine of the angle, which gives me mg tangent of the angle. And this is equal to MAC. So if I do that, I get rid of this, I get AC is equal to FC divided by M, which is equal to mg tangent of the angle divided by M, which gives me g tangent of the angle. And depending on whatever angle I have there, we'll figure out what my centripetal acceleration is. Then we can solve for the velocity of the car, because that'll be v squared over r is AC. We get v squared is equal to RAC. We get v is equal to the square root of RAC. And that becomes the safe speed of which to go around the banked turn. And that's how you get your speed limits posted with a degree of safety. All right. I'm sure you have this in your homework. We have a roller coaster. we're given a roller coaster, and we're going to come down into a valley, and we're going to come up here at the top. Okay? We're told the radius of this part is 10 meters. We're told the radius of this part is 15 meters. We're going to be given a car with a mass. Okay, so here's our car. It's kind of or a marble or whatever. It's going to be given a mass. And depending on what your problem setup is, it's going to, whatever that problem is, you're going to be given a mass. And we want to know if the vehicle has this particular speed. So this is point A, and this is point B. We want to know what the force on the track is at point A. And we want to know what the force of the track is at point A. So if I draw at point A, I'm going to draw my free body diagram that I've got. The car will be moving at a mass times acceleration. I've got the force on the track, and I've got the normal force. And if I'm doing my summation of forces, I'm going to have mv squared over r is going to equal n minus the mass times gravity. If I'm solving for the normal force, because that's going to be opposite the other, I'm going to get mv squared over r plus mg is equal to n.
So this is two-dimensional.
Well, we're summing up our forces. Yeah, we're summing up our forces here because I've got my mass times my acceleration. It's got to equal the gravity times that. But it is, so the normal force is equal to the centripetal force, because remember my centripetal force is center seeking. So if I write my centripetal force is center seeking. So I can add that in there, plus the weight of the vehicle. It's another way of looking at it. Because remember, if I'm going around a circle, the force is going to be towards the center.
That's just weight.
Yeah, that's just weight. So that's just another way of setting up your balance equation. Now when you do it for the point of fly off, that's when n is equal to 0. And that gives you the point for something to fly off. Okay? So when you're setting up your problem, that'll give you that point to fly off is set up to 0. And that should get you started on the homework. On Wednesday, we'll start with torque and center of mass and the other condition of equilibrium, no rotation.